So now that we've had a general discussion about continuity, let's look at a few examples and see if we can figure out whether these functions are continuous, and if not, what type of discontinuity they have. So the first function here, f of x equals 4x over x squared minus 4. Let's start out by just graphing it and see what the graph looks like. So we get our calculator up here, and we have 4x divided by x squared minus 4. Okay, always remember to put that denominator in parentheses there. So let's go to our graph and see what it looks like. Now, depending on the calculator you have, you may or may not have these lines that connect this line here with this one and then this line here. Those are actually asymptotes. It depends on the mode you're in too. I can go ahead and change my calculator to dot mode, and it'll create it in dots. And then when you have the dots, it doesn't look as pretty, but it doesn't connect those asymptotes either. I prefer to stay in connected mode, and I just realized that those lines are not actually supposed to be there. These are asymptotes, alright, and so they don't exist. If you have a newer version of this calculator, then those lines probably won't be there. So the question is this function continuous, and if not, what type of discontinuity? You can see here at these values it's discontinuous. We have to go down here, and then we pop all the way back up here and keep going, and then the same thing here. So with these asymptotes, the function goes towards negative infinity and comes back to positive infinity. So it's definitely discontinuous, alright, and it's infinite discontinuity. Now if you want to figure out where, you can hit your trace value, kind of follow it over until you can figure out about where it happens. So it's happened somewhere between negative 1.9 and negative 2.1 because it pops from positive 22 over to negative 16. Alright, and you can actually tell by looking at your function that if you put negative 2 into the function, it'll give you 0 in the denominator, which means that it's going to be this asymptote right there. Alright, and then the same thing with the other side. You can kind of arrow over and see where the positive asymptote is going to be, and this one's going to be at 2. So your two values where it's continuous are x equals 2 and negative 2. So we can say that f of x has infinite discontinuity at x equals negative 2 and x equals 2. Alright. Now you may have just noticed right from the get-go that the bottom here, if you put in positive 2 or negative 2, it's going to be 0. And that's going to cause some issues, and it's going to cause some discontinuities. And that's definitely true. But the type of discontinuity may change. So it's always a good idea to look at the graph. And we'll see an example of that in a minute here. So let's slide up to our second example here. So again, let's put this in our graph and see what it looks like. If you're not sure where absolute value is, I find that the easiest way to find absolute value is it's in your catalog, and you can find your catalog right above 0. So if you hit second, 0, it's the first option there, ABS. Okay, so I put it in a little early there, but that's where it's at if you're looking for it. So 5 minus the absolute value of x and divided by x. So let's see what this graph looks like. Alright, so it appears that we are at the value of 6 for a long time, and then right about here we hop down to 4. So right at that value of 0 there, we have an issue. And again, looking at our function, when you put in 0, you get an undefined answer because you are dividing by 0. So again, that's where you're going to find some issues with discontinuity. So this function is definitely discontinuous at x equals 0. And the type we have here is jump discontinuity. We're going along, and all of a sudden we jump down to a different value, and then we have a new function. So this function here, g of x, has, let's put has, jump discontinuity. At x equals 0. Alright, and then finally our last example. We have x squared plus 2x minus 15 divided by x minus 3. Now you may want to get into the habit of looking at this and saying, oh, this is very similar to the first one we did. We just figure out where the bottom's equal to 0 at 2 and negative 2, and they're infinite discontinuity. There's going to be asymptotes there. Well, be careful with that. Let's graph it just to make sure, and you'll see what happens. So we get to our y equals, type it in. And I think you'll be surprised by the result. It looks like a straight line. Well, obviously something's wrong, because if we put in 3, we're going to get an undefined answer. If you hit trace and you type in the number 3, look at the y value it gives you. It's not even there. It's non-existent. So with this one, even though my graph doesn't show it, what it looks like is it's a line, and then at 3 there's a hole. Okay, and so this is something really neat that happens, and we'll talk more about it in the future when we talk about limits. But this function is no asymptote. There's no asymptote involved, but there is a hole there. So with this one, you get discontinuity at x equals 3, and it is removable. So it's always a good idea to look for when the denominator is equal to 0, then graph it and see what type of discontinuity it has.